Now here we'll consider the two concepts. One is the statically determinate and the statically indeterminate. So how you going to identify the question is a statically determinate or statically indeterminate? Then you have to apply the controlling equations so that your problem will get solved. If the shaft has one end free and the one end is fixed, then it will be called as statically determinate. Or otherwise, if both the ends are free, then just by looking at a figure you can conclude that it is a statically indeterminate, and simple one equation, that is the total sum of the torque must equal to 0 for each section. Then you can draw the torque diagram and you can solve the problem. But suppose we have a shaft here is subjected to one constant load or maybe two constant load. That doesn't matter. What matters is that both the ends are fixed. So if both the ends are fixed here, then you have to apply here one additional equation that is called as the compatibility equation, because the summation of a torque is not sufficient to find out here the torque between AB, BC, that is the reaction torque at A and the reaction torque at C. In general, if the number of the unknown torque exceeds the number of the applicable equilibrium equation, is said to be statically indeterminate. Since here one end is fixed here, we have value of theta A will be equal to 0. The torque at B is provided to you and the torque at C will be provided to you. Known value here is theta A is equal to 0 because it is a fixed support. Then the value of TB they will provide, value of TC will provide. Then there you can draw the torque diagram. Then we have unknown value is what is the reaction torque at A. So reaction torque at A you have to find out, that is the unknown value. Second value you have to find out what is the twist at B, that is theta B you have to find out, and the value of theta C you have to find out. As far as the value of TA is considered, you can apply the equation sigma T will be equal to 0. From this, value of TB is known, value of TC is known, so TA can be obtained. Then theta B we can obtain using the sum of TL by JG for the shaft AB, and theta C we can obtain as TL by JG for the shaft BC. So these two equations already with us for calculation of theta. One additional equation of equilibrium will use, that is the total torque equal to 0. So we have three equations and three unknowns, so problem can be solved. In a statically indeterminate problem, we know that theta A equal to 0, theta C equal to 0, but we don't know the value of theta B. And one torque is provided here at TB. So we have known value is theta A. Because of fixed support is 0, theta C is equal to 0 because of fixed support, and one external torque he must provide you. Whereas the unknown value you required in the statically indeterminate case is the reaction torque at A, that is the value of TA you required, and the value of TC you will require. In addition to that, we require the value of theta B also. So in this case, the TA is unknown, TC is unknown, and one value of theta B is required. Out of that, theta B we can find out either from shaft AB or shaft BC, anyone we can use. So it will be same as TL by JG. One will be positive and one will be negative, so that equation is with us. Second equation of equilibrium is with us is summation of torque will be equal to 0. Maximum two equation we can form here, that is theta B and total summation of torque equal to 0, and we have three unknown. So this equation will give you the sum of TA plus TC. Three unknown and two equation, problem is not solved. So in this case you have to use the additional equation that is called as the compatibility equation. In that case we have shaft 1 and this one is shaft 2. So we have to make the value of theta 1 plus theta 2. Whatever the twist in the shaft 1, almost same twist we have in the shaft 2, but opposite in nature, and this total sum must equal to 0. So this additional compatibility equation you have to use in the case of statically indeterminate problems. This type of problems are simple to solve, and in the case of statically always use theta 1 plus theta 2 equal to 0, and then we can develop here the three equation. Equation number 1 is for theta b, equation number 2 is for torque, and equation number 3 is theta 1 plus theta 2 must equal to 0. So we have three equations and three unknowns, so problem can be solved. Here we have three equations are already known to us. This value of summation of t equal to 0 will give the value of TA. So this problem are much simple to solve as compared to statically indeterminate. So initially I will make a practice to solve the questions which is based on statically indeterminate, and in the second part we will solve the statically indeterminate. We have provided here this figure and we have given the distance between the point A, B, C, D. These are the gears here, and the corresponding torque is also given. At A we have torque is equal to 6 kilonewton meter. At B we have torque is equal to 14 kilonewton meter. At C we have torque is equal to 26 kilonewton meter. At D we have torque is equal to 6 kilonewton meter. Now we are on this side, the gear is rotating in a anti-clockwise sense. So this one is a counterclockwise. This will be the clockwise. This will be the counterclockwise. This will be the counterclockwise. For this case, I will take here counterclockwise as a positive value, and the clockwise will be equal to negative value. We have to find out the diameter of the shaft AB and the diameter of the shaft CD, and he says that both are equal. The corresponding the value of the shear stress permitted is 65 megapascal. The diameter of the shaft BC is given as 120, and we have to find out here what is the shear stress in the shaft BC, and all the shafts are solid shaft here. So first of all we'll develop here the torque diagram, and we'll calculate here what is the torque in the shaft AB, in the shaft BC, and in the shaft CD. So let's mark here the point A, B, C, D. Now remember here this one is a statically determinate problem because both ends are free end here. At point D here we have a torque is equal to TD is counterclockwise, and counterclockwise is positive value, and therefore we'll show this torque in above this. So this value corresponds to TD, and we have value of TD is equal to 6 kilonewton meter. Then between C and D no torque is acting, so the torque is remain constant for the shaft CD and will be same as equal to 6 kilonewton meter. So we have torque in the shaft CD is equal to same as the previous value, which is equal to 6 kilonewton meter. At point C we have a clockwise torque which is equal to 26. So 6 is positive value and 26 will be negative value, so you have to move vertically downward. If you move vertically downward, you have to represent here the torque TC. This value you have to take as a negative value and is minus 26. Then between B and C there is no torque acting, so the torque is remain constant over the portion BC. So the torque in shaft BC will be same as equal to the previous two torque is equal to plus 6 minus 26, that equal to minus 20 kilonewton meter. Only for angle of twist you have to take the positive and negative value. For shear stress you have to always take the absolute value. At gear B we have a counterclockwise torque which is equal to 14. This value is minus 20. Minus 20 plus 14 will be minus 6, means we are below the zero level. So we have TB is equal to 14. 14 and minus 20 is minus 6. That value is remain constant from A to B. So we have torque in the shaft AB will be equal to minus 6, will be kilonewton meter. And finally at A we have a counterclockwise torque of 6. Minus 6 plus 6 will be equal to 0. So you start at 0 and you must end at 0. So this one is our torque diagram. We are ready with the torque in the segment AB, in BC and in CD. Now we can answer this question. We have to find out here what is the diameter in the shaft AB. For that one we can use the torque formula. So we have torque is equal to pi by 16 multiplied by d cube multiplied by tau. This we are applying for AB. So you have to take the diameter AB. Torque in AB is equal to 6 kilonewton meter is 6. Kilo is 10 to the power 3 and meter is another 10 to the power 3. That will be equal to pi by 16 into diameter of AB and we have cube of it. The allowable shear stress is equal to 65. So we can very well solve this and we can find out the diameter AB. He says the diameter AB is same as the diameter CD. That is correct also because torque in AB is same as the torque in CD. Since here we have torque in AB is same as equal to torque in CD. So we will get this diameter is close to 77.8. That will be mm. Second part, we are interested what is the shear stress in the portion BC. So because of a solid shaft here, we have torque is equal to pi by 16 d cube. This time we are interested to know what is the diameter. So we'll consider torque in the section BC is equal to pi by 16 into diameter of BC. We have a cube of it multiplied by shear stress in the portion BC. Torque in BC is minus 20, so you have to use the absolute value is 20. Kilo is 10 to the power 3 and meter will convert into mm will be another 10 to the power 3 is equal to pi by 60 into diameter BC which is given as 120. So we have 120 cube multiplied by shear stress in BC. Solve this and you will get the shear stress in BC. You will obtain the value of the shear stress in BC is very close to 185.18 will be megapascal. A copper pipe has an outer diameter of 40 mm and the inner diameter of 37 mm. So we have a hollow pipe. It is tightly secured at A and the three torques are applied as shown in figure. One is 80 Newton meter, second is 20 Newton meter and another 30 Newton meter. Determine the absolute maximum shear stress developed in the pipe. Since we have the cross section is same, so you have to find out which section has the maximum value of the torque. So we'll label this point equal to B, this one is C and this one is D. So this one is a counterclockwise torque is 80 Newton meter acting at point D. 20 Newton meter is clockwise torque acting at point C and 30 Newton meter is anti-clockwise, that is a counterclockwise acting at point B. Reaction torque you have to find out, and since we are interested to maximum shear tau max and tau max is directly proportional to the maximum torque either in AB either in BC. So we have to first find out which where is the maximum torque. In addition to this, we have given the value of DO which one is equal to 40 mm and the value of DI is equal to 37 mm. So we have K is equal to DI divided by DO is equal to 37 divided by 40. Counterclockwise will take it positive, so clockwise will be negative and counterclockwise will be positive. At point D, we have a counterclockwise torque is 80, so we'll show 80 upward. So this torque represents the TD torque which one equal to 80 Newton meter. No torque is acting from C to D, so torque is remain constant. So torque in the shaft segment CD will be same as equal to 80 Newton meter. At point C, we have a clockwise torque is acting equal to 20. So you have to move downward by 20. So we have value of TC, you have to take is negative value because it's a clockwise is minus 20. Previous value was 80 and minus 20, it will become 60. So from B to C there is no torque acting. So torque is remain constant over the section BC. So this one is representing the torque over BC and this value is equal to minus 20 plus 80 that equal to positive 60. And then we have again a counterclockwise torque equal to 30. Counterclockwise means positive value. So you have to move here by 30 units. So this one is the torque TB and TB is equal to positive 30. previous value was 60, this value is 30, 60 plus 30 is 90. That value remain constant over the section AB. So this one is representing the torque AB, and this torque is same as equal to 30 plus 60 equal to 90. And this total torque is the reaction torque is TA, that is equal to 90 Newton meter. So in the shaft AB we have torque equal to 90, in the shaft BC portion we have torque is equal to 60, and in the portion CD we have torque equal to 80. So in this case the maximum torque will be equal to T maximum in the portion AB, that equal to 90 Newton meter. And now we can use the torsion formula. So we have torque is equal to pi by 16. Since it's a hollow, so we have dO cube into 1 minus k to the power 4 into tau maximum. And we have to select the AB segment of the shaft where the torque is maximum. This value is Newton meter. So we have TAB equal to 90 into 10 to the power 3, that will be Newton mm, is equal to pi by 16. dO cube is equal to 40 cube. So we have 40 cube into 1 minus k value is di by do is 37 divided by 40, power is 4, multiplied by the maximum torque. So only unknown in this equation is maximum torque tau max. So we have maximum torque tau max will be equal to 26.7 will be megapascal. This one is the maximum shear stress. If you ask to find out what is the minimum shear stress, then that will occur on the portion BC, because the torque in the section BC is minimum out of 90, 60 and 80. So just draw the torque diagram and identify where we have a maximum torque, equate that value with the standard torsion formula and find out the maximum shear stress. So we'll continue with the multiple torque problem, and that is a statically determinate. For the step shaft shown here, find the angle of twist at A, which is a free end, and C is fixed in radian, and the value of G is given as 40 gigapascal, and we have to consider it's a solid shaft, diameter and length are given. So first of all, we'll draw here torque diagram. We'll find out what is the torque at section AB and BC. As view from this side, we have 10 kilonewton meter is a counterclockwise torque. Counterclockwise will take it positive, and 20 kilonewton meter is also counterclockwise torque, that will be also positive value. So we'll just project this line and we'll draw here two torque at A and B. This shaft will mark as 1, that is the shaft number 1, and shaft number 2. We'll have a point A, point B and C. At A we have positive torque to be shown is 10 kilonewton meter. So we'll move vertically upward. So this arrow represent here a torque at point A, which is equal to 10 kilonewton meter. Between A and B no torque is acting, so that will remain constant. So between A and B torque is remain constant, and this torque is equal to T2 torque, which one is same as equal to 10 kilonewton meter. Then at point B another additional torque is applied is 20 kilonewton meter is, so you have to move vertically upward by 20. So this vertical represents here a torque at section B, which is equal to 20. No torque is acting between B and C, so torque is remain constant between B and C. This one is torque T. We have previous value is equal to 10, now 20. So T2 value will be equal to 30 kilonewton meter. The reaction torque at point C will be equal to 30 kilonewton meter. 30 kilonewton meter. Since we are moving downward, it will be clockwise. Total value of theta will be equal to theta 1 plus theta 2. Out of that, theta 1 is nothing but TL by JG for shaft 1, plus we have TL by JG of shaft 2. J is equal to pi by 32. d to the power 4. So we have torque in shaft 1 is equal to 30 kilonewton meter. 30 kilonewton meter is 10 to the power 6. Length is equal to 300. In denominator we have pi by 32, so 32 will shift in numerator. Divided by diameter is 40, we have 40 to the power 4. And we have value of G is equal to 40 gigapascal. We have to use in megapascal is 40 into 10 to the power 3 plus torque in the shaft 2 is equal to 10 kilonewton meter is 10 into 10 to the power 6. Length of shaft 2 is equal to 200. 32 in the denominator will come in numerator. And the diameter of the shaft 2 is equal to 30. So we have 30 to the power 4 into G value is same 40 into 10 to the power 3. Both these torque are positive because they are above. So if you construct a diagram above the zero reference, you have to treat both value as a positive value. So in one step, we will get the total angle of twist with respect to C is equal to 1.52 radian. You require the answer in radian, so you have to give the answer in radian only. The video you are watching is from the app, which is the Mohod class app available on Google Store. And in this app, we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.